So good evening, everyone. I'm going to present you the webinar for today, which is on 3D metallic printing with Zetamix. So my name is Frédéric Rousset. I am a materials engineer at Nanoe, and I am specialized in 3D printing. So I'm going to share my screen, hopefully. Hopefully you can see everything. Just to check if everything is going all right. Okay, so as I said, I'm going to do this webinar on metal Zetamix 3D printing. So first of all, I'm going to do a quick presentation of the company, so a few words on it. So the first thing you have to know about Nanoe is that it is a medium company. It is a production of raw material, so oxide powders mainly, some ceramic powder production. So we have some alumina and some zirconia, but we have other materials as well. You have to know that this company is more or less pretty recent because it has been created around 12 years ago. And now we are focused only on mainly on innovation. So you have a couple of new material developments, as well as a centered R&D. And recently we are a bit more focused on 3D printing materials. But the company is focused on innovation for the production and some 3D printing. For the customer processes that we have, you have a couple of processes available. We have 4 different processes. So 3 of them are some traditional processes. You have the pressing, the casting, and the injection molding. And most recently, you have the new technology, the 3D printing, that we will present to you on this webinar today. So those 4 are the shaping process to obtain your parts. And after that, you have to sinter the parts. So this is a very high temperature process that will densify your parts that you need. The different applications that we have at Nanoe. So the most common ones that we have are the aerospace, the biomedical, and the semiconductors. But we also have some fluid handling, as well as wear parts and tooling. But of course, we have also some aesthetics parts like jewelry or watchmaking. So this was the brief introduction of the company, and now I'm going to dive a bit more on the subject with 3D printing. So I'm going to remind it very quickly that Nanoe is a company that is working on the production of raw material, which means we are quite a bit different from other companies that we have that are on the markets. Other companies are more focused on the printers to adapt the printer to the material, but we are a raw material production. So we are going to adapt the feedstock, the filaments that we have to the 3D printer, which is pretty amazing because you can print all filaments in every other printer that you have on the market, which is the purpose. So I'm going to develop this a bit on the core competencies that we have at the company. So as I said, the feedstock is the main focus here. It is the blend of a powder, so ceramic or metallic powder, that is over 50% in volume, and you're going to mix it with different thermoplastics. So some binders, you have a couple of binders depending on the formulation that you have to need. You have the backbone, you can have some plastifiers, some dispersants, and all of those binders are melting at a very low temperature, which is why you can print your filaments at a very low temperature on the 3D printers. So at Nanoe, we are making those highly loaded central filaments, and those are the different materials that you have available at Nanoe. So you have 3 different ceramics for now and 2 metals. So for the ceramic, we have alumina, white and black zirconia, and for the metals, you have the 316L, which is the stainless steel, and the H13, this is the tool steel. So now I'm going to just quickly present you the offer that we have at Nanoe. So we are selling a package that is starting around 10,000 euros. In this package, you have three different things. You have the printer. The printer is a 3D raised 3D. Then you have the debinding kits and the sintering furnace. So this is starting at 10,000 euros. And of course, we are selling some material with it, with or without it. And depending on the company, sometimes you don't have to need a debinder kit because you have one, or same for the printer. If you want to use your printer, you can, and you can just buy the rest of it and the material that you need. So we have two different materials here, so the ceramic and the metallic filaments. On this webinar, we're going to focus more on the 316L, so the stainless steel and the tool steel, which is the H13. So I'm going to develop a bit more on the different processes depending on the material that you have. For the ceramic, so alumina and zirconia, you have 4 different steps. So for those 4 different steps, you have the modeling, of course, then the printing, then you have a chemical debinding that you have to do. And after that, you have the sintering. So for the sintering, it is in the Zetamix, which is working very well for all of our ceramic. Then for the H13 process, so the first metal that I'm going to present, you have all those processes, all those steps, but you don't have any chemical debinding. The debinding will happen in the Zetamix while we are sintering, so at a lower temperature. But it removes a chemical debinding step, which is quite nice. And the last one is the 316L. It is the same as the H13, but you cannot sinter in the Zetamix your pieces. You have to use a furnace that is using hydrogen in it. So now I'm going to do a quick presentation of the 5 preparations. So for this webinar, I'm going to do a presentation on the H13. So I'm going to take a little piece. I'm going to take a gear. So this is the piece that I'm going to show. So I'm going to do a quick overview over the parameters that we have. So first of all, the first thing that you have to do while you are on this slicer, the slicer is Idea Maker. This is the slicer that is used for Raise 3D, but it is an open source slicer, so you can use it with any other printer. So first of all, you have to do the scaling of your piece. So the first thing you have to do, and I know the scaling, of course, for the H13, but those are some values that we are providing, of course. So this is the value you need because you will have a shrinkage after the sintering. You have to scale up a bit your piece if you want to have the right dimensions after it. So of course you can move a bit your object if you want on the bed, sorry. Then you're just gonna slice it. So those are the different I have. This is for the H13 that I'm using right now. This is for 0.6 nozzle. I have all the parameters set in. The parameters we are giving them as well. I'm just going to slice it without touching anything. So this piece is around 1 hour and a half. I'm going to do a quick preview of the piece, of the parts, just to explain you quickly so you don't get lost a bit when I am explaining the different parameters that you have. This is just the skirts, just to see if the filament is extruding well before starting to print your piece. So 3D printing, you are going to do it layer by layer, of course. So in yellow, this is the infill. So you have to do an infill. You can do this infill that should be around 100%. You can have different patterns of the infill, of course. You have different layers. So the shells, you have 1 outer shell and 1 or 2 inner shells. I'm going to dive in this more after I'm explaining the different parameters. And you have 5 bottom layers, solid bottom layers, so that your part is well closed, as well as 5 top layers. You cannot see them, but they are 5 top layers. So right now, I showed you the preview. I'm going to show you a bit more the different parameters that we have. So the parameters that I have put in this template is for the H13 for a nozzle of 0.6. So it can vary a lot depending on the size of the nozzle you're using or the material, of course, but this is for the example. So I'm going to show, I think I'm going to show about 10 different parameters. There are a lot of them, but I'm just going to show the most important ones. So first of all, I'm going to show the layer heights. So the layer height is very important. It is depending on the nozzle that you are using, of course. You can go, so I'm using 0.2 for now. You can go from 0.1 to 0.4, depending on what you're using. For the shells, I'm recommending 3 shells. This is the best. You can do 2 shells, but it can be a bit brittle. So I recommend 3 shells for the H13. So this is it for this part. For the extruder, the extrusion width, it is set at 0.6 for the H13. You can go from 0.5 or 0.4 to 0.8, depending on the size of the nozzle. You want to that it is a bit more than the size of the nozzle, so it can smash a bit more on the bed. You don't need any retrotraction for the metal. You don't use some retrotraction because you're going to do some back and forth in the extruder and you don't especially need it, so it is safer to not do it. For the infill, you have a couple of different things from the infill. So I have set for now 100% on the density, but of course it is depending on the piece you want. It can go to 20% to 100%. So this is depending on the speed that you want to have your the timing that you want on your piece, or the for some aesthetics reasons. You have different patterns that you can use. The patterns will have an impact on the mechanical properties, but you can have also some aesthetics reasons, which is quite nice. For the solid infill, for the bottom and top solid layers that I have talked about, I will set them to 5 each, and don't move that because I think it is quite nice, quite good. For the platform adhesions, a skirt is way enough because you don't need anything else. You don't have any problem of adhesion on the bed with our filaments on the H13, so don't need to take anything else. For the cooling part, you have to do a maximum fan speed at 100% so that you can cool your part quite quickly. This is important. For the different temperature, for the extruder, you are at 180 degrees, so this is below 200 degrees. So most of the printers can do it quite easily. For the heated bed temperature, it is at 30 degrees. It is very low. This is very good because some printers cannot go over like 80 or 100 degrees on the bed temperature. So this is very important as well. For the speed, I would recommend 20 millimeters per second, but of course you can vary that depending on the accuracy that you want on your piece, or if you want to print it faster, this is depending on what you want. So this is quite all of the different parameters that are very important. Of course, there are many other parameters, but I cannot go over them in one webinar, of course. So this was for the parts on the slicer. So now I'm going to go back to the printing. So I'm going to show a little video of the printing that we are doing. I have it right here. So this is me again. So this video was made with black zirconia, but it is the same with other filaments. It is the same process. Don't have anything to change at all. So I'm putting the filaments on the Race 3D, and I'm going to load it on the top of the extruder. I'm going to load it at 180 degrees and wait till it gets to this temperature before loading. This is just to show how I will put it inside and tighten the screw. I think I will have a quick zoom just to show, because this is the part where you have to tighten it correctly so it doesn't attack your filaments, it doesn't squash it or smash it. So this is in real time. It is taking a bit of time, but this is the time that you need to print your objects. We haven't done any cuts for this one. So I'm just going to load the filament at 180 degrees once it is in the gear. We'll have a quick move, a quick zoom to show the filament that is loading in a spiral, just to check if it is loading correctly and there isn't any clog in the extruder. So I'm doing the bed leveling. This is very important so that the first layer is well deposited on the bed. I'm using a metallic pot just to set the bed leveling. So this is a really important part. Can be quite sensible depending on the filaments that we are using. You have to get a little hand of it. This is the only part where it is you have a couple of hours or minutes to get a hand of it. So I'm redoing the bed level so that the metallic part I am inserting just so it can grip a bit, not too much, so the first layer can go on the bed without any problem. So if I have done this correctly, it should grip a bit when I'm doing the demo, I think. Yes. Okay, so you can see it grips a bit. That's what I want to print the parts. So this was just for the printing part. After you have done your bed leveling, you just have to print your part that you have on your USB. Then after this, I'm going just to show the sintering parts. So for the sintering part, I also have a quick video on it. And it is again me who is showing this. So for this video, I have to tell you, this is a video for ceramic. For the metallic parts that you are using, you will need to have a flow of argon. So I'm going to put the piece at the center of the furnace, which is quite important to put it at the center. And I'm going to put some thermal shields so that the temperature is even inside the furnace. And I can close it. So when I'm closing it, it is mainly useful for the metallic parts where you can see you can put a flow of argon in it. I'm going to set the cycle temperature. So those are the cycles that we are giving out also, of course. A little time lapse, and that is where you can take your part out after a couple of days of sintering. And depending if it is ceramic or metallic parts, you have to do the demining or the sintering in the furnace. I'm going to take out the thermal shields and, of course, the part that you have. So if it has done correctly, you can see quickly that there is a bit of a shrinkage for the piece after the sintering. I'm not quite sure you're going to see it. I'm going to show it very quickly. So, but take my word. It is shrinked a bit. So that was the part on the sintering process. And lastly, I'm going to show you detail a bit the key benefits of the Zetamix. So we have 4 different points that are very important at Nanoe. The first one is that it is an easy-to-use system. FDM is quite easy and everybody can use it. The training day is around 1 day before you can create some good parts. So it is quite quick and very easy. The second point that is very important is the investment that is very low. So as I said before, the package is starting at 10,000 euros. So for this package, you have the starting, the training, the user guide. You have the 3 different pieces that you need, like the 3D printer, the debinding kit, and the Zeta Sinter. And you have some material that are provided with it, of course. The third point that is important is the versatility. We have a lot of materials that are available. We have a couple of ceramics and now a couple of metals. So mainly alumina, white and black zirconia, and the 2 metals that I have explained before. And of course, we are a company of innovation. So in development, we have a couple of materials like silicon carbide and others. We are always open to test out some new materials and try to adapt it to the printers on the markets. The last part is the great accuracy that we have. A lot of people can think that FDM isn't quite accurate, but it is very good depending on the part that you need. Of course, it is not comparable to SLA in terms of accuracy, but you can go to 0.15 millimeters for parts up to 80 millimeters. So this is a very good accuracy for the process. And of course, the benefits of the 3D printing is that you can print closed properties or hollow structures that are quite difficult to do or even impossible to do with traditional processes. Oh, yep. Okay. So now I'm going to dive a bit more on the subject of the material selection. So in which case you should use which filaments in all the materials that we have available at Nanoe. So first of all, I just want to do a quick reminder that the ceramic could be a bit harder to produce with conventional processes, but with 3D printing, it is much easier with ceramic or metal. You don't have any difference, so it is not parameter that you need to worry about. So after that, I'm going to present the different questions that we have to select the material that you need. So if you need some high resistance temperature, you can use the alumina that goes up to 1080 degrees. If you need to go lower, you can use the H13 at lower than 600 degrees if you need to have an additional parameter property like impact resistance or electrical conductivity. For the thermal conductivity, you also have to use the alumina. This is the best one, the ceramic one. And of course, if you need as well other properties like impact resistance or electrical conductivity, you can use the tool steel that is very good as well. For any electrical insulation, you can use the alumina. There are no questions about that. For the electrical conductivity, you can use the metals that we have available at Nanoe. For the high impact resistance, the best ones are the metals, so the stainless steel and the tool steel. If you need to have a high temperature resistance, so over 600 degrees, where the metals are a bit less advantageous, you can use the zirconia. And if you need some corrosion resistance, you can use the stainless steel. So for high mechanical loads, you can use the metals, as well as if you need some ductility. For the ductility, you can use the different metals, but if you need more corrosion, you will use the stainless steel. If you have an environment that is quite hot and humid, so over 80 degrees with water or some steam, you use the alumina as first, the best material that we have. You can use the 316L for the fact that it has an impact resistance and some ductility, and it can resist to hot and humid environments. For any wear resistance, you have to use the ceramics. So alumina or zirconia, the best one is the alumina. And of course, as always, if you need additional properties, you will need the H13 for impact resistance or others. For the corrosion resistance, you will need, as always, the ceramic parts that are the best. If you need additional properties as well, the 316L is resistant, a good resistance at corrosion as well, with other properties that you need. So after that, I'm going to just present two use cases that we have at Nanoe for now. So the two use cases that we have, the first one is the Zetamix extrusion die. So a couple of weeks back, we were trying to think about having different extrusion dies with different filaments to develop new filaments or to test out new things. But with conventional processes, it can be quite long to have them. And we thought, why not print it at Nanoe with our printers? So we printed it in H13. So this production, you have to know, it can take less than a week. So this is very important because the regular processes can take over a month to have them. So if you want to have very quick dies, it is better to do in 3D printing to have them highly customized, because you can change the angle of the cone, the diameter, or the length of the die. So this can improve the R&D process because you can do it quite quickly, and you can have the possibility to add a static mixer as well in the extruder. The last use case that I want to show is the Zetamix mold. So we need heat resistance parts as well as elasticity. The fact that we are 3D printing it is better with cutting down the delivery time. So for regular processes, it can take 4 to 8 weeks to have a mold. And so we made it in H13 as well. The parts cost around 30 euros. It can be made in 1 week, of course. You have the possibility to produce complex parts in it. This is why it is very important in 3D printing. You can do some inscriptions on it, but you can add some internal channels to cool the mold faster. You can do it by machining it, but with 3D printing, you can do some more complex internal channels in the mold, which will help a lot to cool your mold faster. So this was the last use case that I wanted to present, and this is my last PowerPoint. Thank you for watching. This was my first webinar, so I hope I did my best. I will answer all the questions that you have at the end, of course. So right now, if you have some, you can write it in chat. I'll be happy to answer them. If I can't answer them, I can redirect you to an email so that you can have the answers that you need.
Thank you very much, Frédéric, for the presentation. So we do have a few questions. I'm just going to read them to you, and I'll leave you to answer. The first one was, can you say a bit more about the time for 316L and H13 sintering? does it depend on part dimension, and how long is it?
For the time, it's about 4 or 5 days, I would say. Just for the sintering, it could be 4 days. And you're doing the debinding with it in the furnace, which is quite important. You can do the debinding and the sintering as well. So it shouldn't be over a week, that's for sure. And depending on the parts on dimension, the parts on dimension will be maximized with the size of the furnace. You cannot print a part over a certain size depending on the furnace that you have.
That was another question just after that. Which was what is the largest part that you can?
The largest parts. What are the largest parts that we have done? We have done some quite large parts, but I can't quite remember which one was the largest that we have done.
What would be the limit? I mean, for a standard part.
I haven't done the limit yet, so I guess
the limit of the furnace itself.
Yeah, it's the limit of the furnace. It isn't really the part; it's the furnace. It has to be heated pretty evenly. So, so this is the limit, more or less.
A question about the structural strengths of the parts after printing and sintering, and can it be used in aerospace and automotive applications?
I'm not quite sure on this one because I haven't done any tests on the structural strengths of our filaments. We have done this on ceramic, on our zircon, but not yet on the H13, which is quite recent. Well, I'm not sure. Maybe some people, if you could send this question by email, maybe someone can answer them better than me.
A question on the volumetric load of ceramic and metal. How much ceramic and how much metal is there in the filament?
Oh, the percentage in volume. So for the ceramics, I don't quite remember for ceramics. I'm working a lot of metals. But for the metals, it is 52% for now, which is quite well. And for ceramics, I don't know if you know, Guillaume.
Something depending on the material, it's 50 to 60, but I don't have the precise value.
Yeah, it's never below 50% in volume. So more or less between 50 and 60.
Can you combine, I like this one, can you combine metal and ceramics during printing and sintering the complete part? Can you make a multi-material part in ceramic and metal?
You could do that. The difference, the hard parts in it will be sintered the parts after that, and to retract the parts in that you need. You can do it, I think. The only problem that you have with that is that you have to take into account that you have a shrinkage property between metallic and ceramic that is not the same. So you have to take into account when you're printing the object, the shrinkage in ceramic or in metal that you're using for the parts.
What is the max temperature and part size in the sintering oven we offer?
The max temperature in the furnace, I think it's 15 degrees. And the part size, I'm not quite sure for the part size.
Well, the tube is what 100 millimeters, something like that.
Yeah, something like this. Yeah.
Yeah, the tube is 100 millimeter, so it needs to fit into the tube.
Yeah.
When that one was answered. Will you be developing materials that don't need the debinding step? Well, actually, you answered it during the
will you be developing materials? Yes. Like the metal, the debinding step, no debinding steps.
No, it means no chemical debinding.
Yeah, no, okay, no chemical debindings. Yes, of course, the 813 and the 316L that we have, you don't have any chemical debinding steps. The debinding is thermal, so it is in the furnace. You have the thermal and the sintering in the same process. You will just have different ramps depending on the temperature that you need for debinding and sintering.
Questions from Scott on the kind of printing surface we're using. Is it built tack or something different? What do you print on?
When do we print on?
For the plate, what kind of plate do we use?
It is a ceramic plate. I don't know in which material.
No, I mean for the printing.
On the Race 3D?
Yeah.
The bed, it is a simple plate. It is a flex, how do we say it?
Yeah,
flexible plate.
So that question was already answered. This one also. Have you tried printing the model at an angle? You would reduce the effect of the layer lines.
We didn't try it yet, but we could try it. It could be a great idea. I will keep it in mind.
That one we answered. What is the amount of porosity after sintering with 316L?
The 316L, I think it is over 90 in density. How much is it exactly? You can ask by email because I don't have the exact value, but it should be maybe 95 or something like this. I don't quite remember.
Yeah, something in that range.
Yeah.
5 to 10% of porosity depending on the sintering.
Yeah.
What is the max build volume of the printer itself?
On the Race 3D, quite large. Depending on the model you have different models of Race 3D. But the one we are selling out with the package, I don't have the dimensions on it, but it is quite easy to find.
It's 300 plus 300.
Yeah. Okay.
It's a cube of 300. A question about supports. How do you support the parts, the metal parts? Do you use the same material? Do you use a different material?
You can use the same material, but you have to remove this part after sintering. So you have to do some machining to remove it. You can try to take other materials like PLA. That is possible, but you have to keep in mind that you have to take those hoopers backs after the sintering parts. So depending on how you want to draw them back.
Do you recommend to clean the part after print, and do you prefer to do it after sintering?
You don't need, you can need, depending on the part that you have printed, you can optimize the parameters, which is helpful, and you don't need to clean the part. I don't clean a lot of my parts, most not. It is better to do something after the sintering. You can polish it. You can, how do we say, you can sandblast it to obtain a really nice part in surface.
This one was done already. What's the main differences between what we offer and Virtual Foundry or BASF?
Oh, I'm not quite sure.
Do you want me to take it? I'll take this one then. So it's two different products. If you talk about BASF has great filaments. They have one drawback in terms of technology. It's a filament based on POM, which is a material that is used for catalytic debinding, which means you have a separate step after printing where you put the part into a very specific furnace under nitric acid vapors. Basically, it makes the process a bit complex and quite expensive in terms of investments. You don't have any system for doing that at the kind of prices we can offer. Virtual Foundry is again a very different product. It's a product with a, let's say, lower content of of metal by volume, so it doesn't really make dense parts. You can sinter it, but usually you need to put it into a powder bed or something, and it doesn't actually get to a good density. So I would say really 3 different products. Virtual Foundry for me is more for the consumer market. BASF is really for industries, for industrial who already have the equipment, and we're trying to fit something in between. We're trying to fit the need for professionals that don't have the equipment yet, so who want to invest in let's say reasonably priced equipment, and that's what we fit where we fit in at Nanoe. A question on difference in the binding of metal and ceramic. So what are the differences?
Yes. Yeah, the differences have explained it a bit more or be a bit more clear. So for the ceramic parts, mostly for now, there are some chemical debindings that you need. But for the metallic filaments, you debind it thermally. So inside the furnace, you don't have any chemical debinding for metals. This is for 316L or for the H13, both of them.
Could you also elaborate a bit, that's my question, but on the difference in sintering between H13 and 316L?
Yeah. For the sintering parts, for the H13, it is inside our furnace with argon, a flow of argon, but with the 316L, the sintering is made in another furnace. You cannot do it in the Zeta sinter, in the furnace with hydrogen.
So that means more professional equipment.
Yeah, of course.
Again, a question on supports. If you support your overhangs with the same metal filaments, does that mean that at the end of the sintering, the support is welded to the part? How do you remove it?
By machining, I think. Yeah. I guess the machining is the best process to do it. So this is why you can avoid doing as much as supports as you can by try to modelize your parts. I think it's for 3D printing and not for other processes. This is very important. So you don't have to do any supports and avoid it, of course.
So the way to deal with supports is to not make any supports.
Yeah, of course.
So do you use only pure ceramic filaments like alumina zirconia and not filaments like porcelain or other complex ceramic composition?
For now, I am not working on it. I don't think we have some at Nanoe yet.
No, we don't. For the moment.
But maybe in the future.
Yeah. What is the cost of the technology?
So the package is starting at 10,000 euros for all the binding kits, the printer, and the furnace. And you have all the available materials that we have with it.
Okay. Thanks. And this one you already answered also. All right. For the moment, that's all. I don't know if anybody has any other questions. Yeah, we'll send a recall for those who need it, of course. Well, thank you very much, everybody. Thank you, Frédéric, for the great presentation.
Thank you. First webinar. You're welcome.
Well, thanks, everyone. And of course, if you have additional questions, you can contact us by email, LinkedIn, and you should follow our account on LinkedIn for the next webinars.
Thank you, everyone. Have a nice day.